All right, so your floating stability lab is due in lab today, and I've got the lab times listed there. We're going to start lab 7, flow visualization, and I've got a real treat for you there. It's the first lab group in like 6 years that had a fresh needle for the flow visualization lab, and you'll see why that's important when we're in there, but just know that's a huge upgrade. You got a fresh needle. Yeah. So 2 and 3 o'clock for that. Your next homework assignment is due on Thursday, and we'll have a brief little quiz on Thursday just to celebrate the fact that you're submitting your homework. And because we've only had 2 quizzes so far in the semester, and we're already at class 13. We're, I think, more than a third of the way through the semester. We need to have more quizzes, or else any single one of them will count as too much of a fraction of your quiz grade. So that's why we're having a quiz on Thursday. We're going to talk about fluid acceleration today, and as we work through the next few lectures, the main question that we're going to ask when we apply the principles of fluid acceleration is, how does the pressure change as a result of some sort of motion, as the fluid moving around? Before we get into that, pressure changes as a result of fluid motion, let's just review some of the definitions that we emphasized in class last time. First of all, steady flow is when the velocity is constant with respect to time. And you'll remember that uniform flow is when conditions are constant with respect to position. And what grows out of that is a differentiation between local acceleration and convective acceleration. We did an example in class last time that's based on convective acceleration. We were finding out what was the acceleration at a certain point in a nozzle where the velocity was changing because the flow was non-uniform. Remember, non-uniform flow is when along the flow direction the velocity is changing as a function of position. And so convective acceleration for a certain location, if you want to know at a point what is the acceleration, you have to know the velocity at that point. But you also have to know what is the change in velocity with respect to position, dv, ds. And that's the process we worked through in class last time with that example. Now, local acceleration, by contrast, is just acceleration as you remember it from physics class. It's how the velocity is changing with respect to time. And so local acceleration goes along with unsteady flow, and convective acceleration goes along with non-uniform flow. When we expand the concepts behind local acceleration, that's what will give us Euler's equation. And then when we expand the concepts behind convective acceleration, that's what will give us Bernoulli's equation. And those are 2 of the biggest ideas in Chapter 4. You could say that actually Chapter 4 is sort of the pinnacle of the course. Everything was leading up to Chapter 4, and then everything after Chapter 4 is immediately related to specific lessons that are in this chapter. And so it's maybe the most important chapter in the whole book for you to read the definitions that are in there, read the author's attempt to explain things, because you may need more than one point of view on this material. Me explaining it during 75 minutes twice a week isn't going to be enough for you to understand it. You shouldn't expect to understand these concepts just based on what I tell you. It's going to take you also reading the author, thinking about it on your own, doing the homework problems. And so Chapter 4 is really an important part of the course. Euler's equation, as it says here, arises out of applying local acceleration. And it asks the question, how does the pressure change when fluid is being accelerated with respect to time? Now, hydrostatic equation already told us how fluid behavior affects pressure, and the fluid is stationary in the hydrostatic equation. And there is an acceleration in the hydrostatic equation, it's just that it's only gravitational acceleration. And when we had a tank of fluid and we were finding out how the pressure changes as we move downward through that tank, here's the liquid, and we knew that delta P equals delta H times the unit weight. So the way that you'd apply this is you'd say, here's location A, here's location B, and we'd want to know, what is the pressure at B? And so maybe you're knowing that the pressure at A is atmospheric, and you'd find out how far apart they are, and you'd want to look up the unit weight for the fluid. So there is an acceleration term in a static fluid, but the acceleration term in the hydrostatic equation is gravity. And if we rewrite the hydrostatic equation as delta H times the density of the fluid times g, then you can see, here is the acceleration. Pressure is changing because of gravitational acceleration in the hydrostatic equation. Euler's equation just extends this idea that pressure changes because of an acceleration, but now we're going to have accelerations besides gravitational. And that doesn't mean like in different gravities. This Euler's equation, it's not like it's limited to Mars or the moon. It'll actually tell you what the pressure behavior is when you have a liquid on Earth, and so it's being acted upon by Earth's gravitational acceleration and then also some additional acceleration, either up and down. It can be a vertical acceleration or it can be a horizontal acceleration or some combination. So, for example, what if you had a tank of water and it was accelerating upwards at 9.81 meters per second squared, and we want to know what is the change in pressure between the surface and some point 1 meter under the surface. What would be the pressure at this location 1 meter under the surface if we had it accelerating up at 9.81? So now think about it in like physical terms. When an astronaut is being blasted off into outer space, they feel this additional pressure on their head and their back. You know, the acceleration is sort of pushing them into the seat as the astronaut's being blasted upward. So now think about this water. It's being blasted upward at an additional g. So just normal g would mean that 1 meter under the surface you would have, so if it was just ordinary acceleration, the delta H is 1 meter, and the unit weight is 9810 newtons per meter cubed. And so the pressure would be 9810 newtons per meter squared. But if it's accelerating upwards, then that g that goes into the unit weight effectively doubles. And so what we could say is if acceleration upward at 9.81 meters per second squared, then what we are essentially doing is saying that the change in pressure is 1 meter because of the depth. It still has a density of 1,000 kilograms per cubic meter, but now the acceleration is 9.81 meters per second squared plus 9.81 meters per second squared. It's gravitational acceleration and then the upward acceleration of 9.81 meters per second squared. And so the delta P would be 19,620 newtons per meter squared. That's what the pressure change would be if it was accelerating upwards. It's basically doubling the pressure change because you've doubled the acceleration that it's experiencing. If you accelerated the tank downward, that's when the change in pressure would be 0. I guess it depends on the frame of reference. The frame of reference here is how is the liquid experiencing the effect of Earth's gravity. The gravity may be downward, but we know that pressure increases as we go down. And so it's effective as though as though the liquid is being accelerated up. Yeah. The thing that we're going to we're going to know is always true is that the pressure increases in the opposite direction of acceleration. And so think about it this way. If we had a tank of water fully enclosed, so we've got water in here, and I've got 2 points. I'm going to call it A and B. What if I accelerate it this way? So an acceleration causes a change in pressure. Will the pressure be bigger at B or bigger at A? This is not a trick question. They're not going to be equal, because if it wasn't accelerating to the side, then they would be equal. But now we're accelerating it to the side. So the pressure at A is going to be bigger than the pressure at B. So pressure at A is larger than the pressure at B. And so the main lesson is that pressure increases in the opposite direction of acceleration. So when it comes to a static fluid, like when we are saying that if this is B and this is A, we know that pressure at B is greater than the pressure at A because it's below there. So the pressure is increasing, then the effect of gravitational acceleration is as though it's accelerating up. Yeah?
Now, in this case here,
this case here?
Gravity is not affecting this because it's normal to the...
There's still gravity here, but the change in pressure between A and B is affected only by this sideways, the x direction acceleration. Yeah. So if we said, what about location C? Well, let's make it even more interesting. Let's put it between here. All right, here's location C. So and it's still gravitational acceleration applies. So we know that the pressure down here is greater than the pressure at C, but unless we know the magnitude of this acceleration, it's possible that that the pressure at C could be greater than the pressure at B, even though it's higher up, because maybe that sideways acceleration has a greater effect than gravity. So the Euler's equation that I'm going to present to you today has a way of keeping track of both the side-to-side acceleration and the vertical acceleration simultaneously, all in the same equation. So it will be sensitive to that effect that you bring up, is that there's still gravitational acceleration even when it's accelerating to the side. So Euler's equation comes from looking at an element of fluid, meaning just, in a tank of water, grab a certain element of fluid. Here's our element of fluid. It looks like a cylinder, but it doesn't necessarily have to have a cylindrical shape. It's just, in this case, we're going to say we've got some element of fluid and it's a certain volume, and so it's got a certain weight because of its volume and because of the gravitational acceleration. There's pressure acting above the fluid element and acting below the fluid element, and so it's being compressed by the pressure that's applying. It's got a certain delta L, the length of the cylinder. If we find out what's the mass of the object and find the difference in forces acting on either side, then the pressure changes because of how it's being accelerated. And so F equals ma, what that means is that you look at the change in forces, and a force, remember, is the pressure times area. Now, the pressure changes because of hydrostatic equation, but if we take a fluid element and we start accelerating it side to side, we can measure a change in pressure that isn't related to gravity. And how much we're accelerating it determines what the change in pressure is. And so if A is constant, if we just have this element, an imaginary, think of it as like an imaginary shape inside of water, and we have an area that's fixed on either side of it, and we start accelerating this tank left and right, we can measure the change in pressure, and it's going to be directly related to the acceleration that we apply to it. Now here's Euler's equation. On an equation sheet, if I provided an equation sheet for an exam, this is what it would look like, but strangely enough, this actually has to be transformed before you can use it in problem solving. You can't start substituting values in at this point. You have to make an assumption about a linear change in the piezometric pressure. What this says is that the piezometric pressure between 2 points that are delta L apart is, it can be calculated by the density of the fluid multiplied by the local acceleration. L here just happens to mean along the L direction. It can be vertical acceleration, it can be horizontal, but if we assume linear variation in the piezometric pressure between 2 points, then this partial differential just becomes the change in P plus gamma Z for the x direction, the 2 points that are delta x apart, and then we'd multiply it by the acceleration in the x direction. And so then this further expands into, we've got 2 points, 1 and 2, and 2 is always going to be, when you're selecting the points, it actually matters what you consider location 1 and what you consider location 2. I'll go through the process of illustrating for you how you calculate which is which, but it's important to remember that the sign convention here is that location 2 is selected to mean the location that has whatever the most L direction is. And so when you're moving from in the x direction, meaning horizontally, then 2 would be the location that's furthest to the right. So remember this tank over here, when we were looking at this, if it's accelerating in the x direction, that means this is location 2 in that formula, and this is location 1. Because location 2 is further to the right. It has, in the x direction, more x than location 1. So that's how you would select this to be location 2 and this to be location 1. If you were having an acceleration, a vertical acceleration, so a sub z, I'm not going to call it y, I'm going to call it a sub z, an acceleration upwards, and then I had 2 locations, here's one and here's another one, then this would be location 2 and this would be location 1 as I substituted into this. And the reason why we have to differentiate between the two is the acceleration is also the sign of the acceleration. Up will be positive, down will be negative. When we're working side to side, to the right is positive and to the left is negative. So here's the sign convention as far as the direction, what's considered positive, and how we assign 1 versus 2. Okay, let's do some applications because this is all really theoretical until we start to solve some problems with it. We've got a truck carrying gasoline. It seems like a strange truck to carry gasoline in, but we're going to do it anyway. And even worse, it's open to the atmosphere at the far left. See this right here? P is equal to 0. That means there's a little vent here. And so it's venting to the atmosphere here. So it's atmospheric pressure. We know the pressure there is 0. And this tank is slowing, the truck is slowing down at a rate of 3.05 meters per second squared. That means the acceleration is to the left. So here we have acceleration in x is this way. We've got a negative acceleration. So acceleration in the x direction is negative 3.05 meters per second squared because it's slowing down. We know the unit weight of the fluid is 6.60 kilonewtons per cubic meter. And so what's the pressure at A because of this acceleration, and then where's the pressure greatest? If this tank was moving at a constant velocity, if it wasn't accelerating, or if it was stationary, then the pressure at A would be 0. It would have the same pressure if it's at the same elevation. But since it's slowing down, that means that the water is sort of being pressed up against this side. You know, if it didn't have a top on it, if there wasn't a lid on this, as it slows down, it would be like sloshing out over the top of the truck. That would be exciting. The gasoline gets on the hot muffler there. But it has a top, and so its pressure is going to increase in the direction opposite of acceleration. So the acceleration is this way, and the pressure increases in this direction, in the opposite direction. That's what we wrote over there. All right, so let's expand Euler's equation here to solve this problem. We would have pressure plus gamma z at location 2 minus the pressure plus gamma z at location 1 is equal to negative delta x density times acceleration in x. So I moved the delta x to the right-hand side of the equation. So as we expand the equation, here's the delta x. Since x is the direction of acceleration, then L becomes x. That moved over to the right-hand side along with that negative sign. The negative sign is also on the right side. And then the p plus gamma z2 minus p plus gamma z1, that is the change, the delta of the piezometric pressure. So the change between 2 points is equal to negative delta x density acceleration in that direction. What we want to know is the pressure at location A. What this is saying is the pressure at A plus gamma ZA minus the pressure at this initial location plus gamma, but it was going to be minus because the negative sign there distributes through. So minus gamma Z at the initial location is equal to negative delta x density acceleration in x. So is everybody with me up to this point? We've just expanded out the left-hand side of the equation, and the negative sign means it's negative pressure at the initial point minus gamma z at the initial point. Okay, so some things that we know is that ZA and Z0 are equal to each other. They're at the same elevation. And so we can cancel this term and this term because they are equal. The other thing we know is that the pressure at that initial location is 0. And so this term drops out. So the pressure at A is equal to negative delta x density times the acceleration in x. All right, so let's substitute in some values. Negative, the distance between the two of them is 6.1 meters. That's how far apart they are in the x direction. The density here for this fluid, we can calculate the density from the given unit weight. The density is going to be the unit weight divided by g. And so that is 6,600 newtons per meter cubed divided by 9.81 meters per second squared. That's 672.8 kilograms per cubic meter. So I'll put the density in here, 672.8 kilograms per cubic meter. And then the acceleration, negative 3.05 meters per second squared. Now, you saw that I give partial credit on the exam, right? Sometimes if you just make a small calculation error, that maybe be -1 or -2. If you forget the negative sign, that's a big error on this. It's not a minor error, that's a major error because that's sort of fundamental to the whole concept of Euler's equation is that you have to be consistent in your sign convention on what is an acceleration to the right and what's an acceleration to the left. And here we put in negative 3.05 because it's accelerating in the direction opposite of our sign convention. Our sign convention says that accelerations to the right are positive. So that's the opposite. And so it's critical that you're really careful with direction on Euler's equation problems. And so that negative sign and this one are going to cancel each other out, and then that's going to give us a positive pressure at A, which makes sense conceptually. If it's accelerating, if it's slowing down, the pressure at A, we just sort of instinctively know the pressure at A is going to be bigger than the pressure at B, because all of that water, not water, gasoline, as this slows down, all that gasoline is being forced up against the right side of that container, and so that's why the pressure is going to be greater along that other surface. The pressure is 12,517 newtons per meter squared. So that's the pressure at A. Any questions about this part so far? Okay, so where is the pressure going to be greatest? Well, we know that at A it's got a pressure of 12,000 pascals, and B is below A. So pressure B is going to be even larger than the pressure at A, because it's got not only the side-to-side acceleration, but it also has the hydrostatic force to deal with. So what you could do is you could calculate this and then add on the additional pressure that you're going to get from hydrostatics. So you could say pressure at B is PA plus basically delta H times the unit weight. But I'd encourage you not to do it that way. That'll give you the right answer. But let's actually do it by starting at 0 and finding the pressure at B. And that's just to show you that Euler's equation simultaneously accounts for gravitation and the acceleration in a certain direction. So let's do it the long way just to make the point of how powerful Euler's equation is. And also because this shortcut method that I just pointed out over here, there are times when you won't be able to do that because the vertical acceleration isn't gravitational. You know, that only works when the vertical acceleration is gravitational, like in this problem. So let's do it the real way for part 2. Okay, so part 2 here. Pressure is greatest at location B. So the pressure at B. Okay, Euler's equation, when we expand out Euler's equation, it is that the pressure plus gamma z at location 2 minus the pressure plus gamma z at location 1 is equal to negative delta x density acceleration in x. And we've expanded it out for an acceleration that's in the x direction, like this problem has it in the x direction. Other times, if it's being accelerated vertically, then we would use, instead of delta x, we'd use delta z, you know, the elevation difference between the 2 points. But here it's an acceleration horizontal. So we've got pressure at B plus the gamma z at B. And I selected B because B has the most of the distance in the x direction. Even though it's below, even though it's lower than this initial location, it is location 2 because we're working in the x direction. So minus the pressure at the opening minus gamma z at the opening is equal to negative delta x density acceleration in x. All right, so we have the pressure at B is unknown, plus the unit weight of the liquid is 6,600 newtons per meter cubed, and the elevation of B is 0, minus the pressure at the opening is 0, minus the unit weight of 6,600 newtons per meter cubed times the elevation, 1.83 meters. So Z naught is the elevation above the datum. We're setting our datum to be the bottom of the truck. And so we said here at the bottom of the truck the elevation is 0, and up above that is 1.83 meters of elevation.
ZB is supposed to be
No, it's 0, because we're saying that if we're measuring vertically, location B has an elevation of 0, and then up here that's 1.83 meters above it. So we're choosing the datum to be the bottom of the truck bed. If it's got an acceleration, then you have to solve this in 2 steps. Yeah. Mm-hmm. All right. So it is equal to negative 6.1 meters is how far apart they are in x direction. The density is 672.8 kilograms per cubic meter. And then the acceleration in x is negative 3.05 meters per second squared. All right, so obviously this term is going to cancel out. We'll have P sub B is equal to 12,517 newtons per meter squared plus 12,078 newtons per meter squared. It's going to be 24,595 newtons per meter squared. Now when we did the first part of the problem, we found that 12,517, that is how much acceleration there is due to the side-to-side acceleration. This is because of it's slowing down. And then this is because of the elevation difference between them. So you could say that this is from 0 to A, and then this is from A to B. But the main point is that Euler's equation actually takes into account both the gravitational, the difference between the 2 points in elevation. That's this part of the equation. Takes the vertical difference into account. And then this part of the equation takes the local acceleration into account. Is that the last handout, and we still got more? No, we got some more. All right. So we can also apply Euler's equation when the pressure is changing in a pipe, like if it's accelerating over time, meaning that we've got unsteady flow. So let's consider a pipe that's horizontally inclined. Now ordinarily, if the fluid is not accelerating over time, then the pressure would be if we neglect the friction effect, the pressure would be the same if it's in the same elevation. They just are some horizontal distance apart from each other. But in this case, Let's find out what sort of a pressure gradient would be required to accelerate the fluid at a rate of 6 meters per second squared. All right. A and B, we're going to say let's have them be 1 meter apart. So Euler's equation, if we have some initial location and a final location, Euler's equation is going to expand out to P sub B plus gamma ZB minus the pressure at A minus gamma ZA will be equal to negative delta x, the density of the fluid, and the acceleration in the x direction. So we want to know the pressure gradient, and the gradient means how much does the pressure change per meter of length between the 2 points. And so let's say let A and B be 1 meter apart. So what we'll have is PB minus PA. That's the pressure change. Now the elevation, they're on the same plane, and so ZB and ZA are equal. So it's going to be equal to negative delta x, the density, and the acceleration in x. If this is water flowing through the pipe, then we know that the density of the liquid is 1,000 kilograms per cubic meter. That's our typical density for water. So the change in pressure will be negative 1 meter, the density of 1,000 kilograms per cubic meter, and then the acceleration. It's accelerating at 6 meters per second squared. Now that's intentionally positive 6 meters per second squared, so that means it's accelerating to the right. So the pressure change here, delta P, is negative 6,000 newtons per meter squared per meter. If you look at the units, a kilogram meter per second squared is a newton, and then so that would say newtons per cubic meter, which is the same as saying newtons per meter squared per meter of length. And since these are 1 meter apart, that's how we solve the problem, is having them a meter apart. So the pressure change is that in the direction of flow, if the acceleration is in the direction of flow, then the pressure increases in the opposite of that. And so PB minus PA will be negative. So that means that the pressure at A is bigger than the pressure at B. If we do B minus A, it's going to be negative 6,000. So the pressure is decreasing in the direction of flow, in the direction of the acceleration in this case. In the first example that we worked, this one, the top of the tank was enclosed. There was a roof on this tank that's constraining the liquid from sloshing around. The pressure still changes, but the liquid surface itself isn't affected by acceleration because it's enclosed in a tank. But if we don't enclose it inside of a tank, you can see how the water level, which would be flat before it's being accelerated to the side, if you begin to accelerate a liquid in the L direction, then it's going to cause the liquid surface to respond to that. And Euler's equation allows us to not only answer what the pressure change is going to be, but it'll also predict what the water level looks like. And if you accelerate the tank to the right, the fluid level increases on the left. And you can prove that to yourself with a glass of water. If you've ever tried to go from the sink to the table with a glass of water that's very full, you know you have to accelerate slowly, because if you move too fast, it spills. The reason why it spills in a glass that's been filled too much is that the water level increases in the same way that the pressure increases in the opposite direction of the acceleration. So if you are accelerating it to the right, the liquid level increases along the left. And the pressure on the bottom of the tank also responds to that. And so if we consider the liquid level during acceleration, the pressure over here at the bottom is going to be larger than the pressure over here because it has more liquid above it on the left side than it does on the right. And so we know that the pressure is affected. Euler's equation tells us that the angle of the water surface, you can see here they're describing the angle as alpha. You can find what that angle is as a function of the acceleration in the x direction. If you had, for example, an acceleration that's equal to 9.81 meters per second squared sideways, if it's accelerating in x, then with the same acceleration as g, so if the ratio is 9.81 to 9.81, then that would give you an alpha of 45 degrees. The tangent of alpha would be equal to 1. So you can measure that angle. You can know what the angle is by the ratio of the horizontal acceleration to gravitational. When we get together on Thursday, we'll do some more examples with Euler's equation. This may be the most abstract part of the whole course. I'd say it's probably the thing that students struggle with the most, so I really encourage you to make an investment of reading through the textbook on this chapter and specifically with Euler's equation. So I've got some homework here for you to pick up. I'll give that to you before you leave or on your way out. That's it for today, though. I'll see you in lab at 2 o'clock and 3 o'clock.